if I begin, so look, it is terrific. This is the first time I've hosted a seminar on Zoom. I think it's great to catch up with people. I'm using the participants thing down the side to see who's here, and I'm using the chat. And if you do, which is those buttons at the bottom, if you do want to make comments and questions for Liz as she gives her talk, if you put them all in, I think Liz will go from about 12:05 to about 12:45, and that will give her 15 minutes to go through those questions and answer the questions. And I think it's potentially more interactive than we have with our face-to-face seminars. The other thing I should say is that Remy's recording it. We record all these for people who can't make them, and so that there's an archive. Look, if anyone has problems with that, what I would advise is don't put anything on the chat and don't say anything, or contact us later if something's happened that you feel really uneasy about. But we do like to record it because we think it's a useful resource, and because of timetables, possibly from around the world or different places, or people have commitments, we like to record it so that it doesn't have to be synchronous. So I welcome everyone. Now, there's a thing about making an acknowledgement to country. Some people don't like sort of formulaic, what they see as tokenistic ones. Other people think it's very important that we respect the traditional owners of the land. I think it's important, but I don't like it being formulaic. What I like to think of is the people. So we're all in different places today. I'm on an area of Sydney in the inner west, which is apparently Gadigal and Wongal people lived here. And I always think about what it would have been like, and they were here obviously for thousands of years, what it would have been like outside today for them, because it's a cold, rainy day, which is probably good for the future because it means a lot of the plants that they tended and looked after and lived off would be doing well in the future. But on the other hand, they would have been cold. And I often think in the modern world, of one of the things that's changed, I'm very seldom cold. But they probably would have been cold, and they would have been a lot tougher than I am. And they lived successfully, thrived for so long, and still do thrive. And our Indigenous community in UNSW adds to our understanding of a sense of place and our connections with the environment. So I welcome you all today, acknowledging the history that we share. The Indigenous history of Australia. So now I want to talk about our speaker, Liz. So look, Liz has been at UNSW for a long time, and she was a PhD student with Victor Flambaum, who is a genius. And I've often wondered how intimidating it must be to work with someone who is so sort of instinctive about mathematics. And I think that Liz managed it so well because I think she is a gifted and highly intelligent academic like Victor is. And, you know, Victor is very selective in the students. So I know that Liz has been with us for a long time. So then she turned her attention to helping particularly with first-year physics, and transforming. First-year physics is one of those subjects which is compulsory for many, many students, and but not all of them are instinctively as adept with it, and people have had different backgrounds. And Liz has done so much work to support those students. She's taken a very scientific approach for seeing what works, what knowledge they come in with, what knowledge they go out with. She's a fellow of the Scientia Education Academy, and this academy shares the best practice. And then Liz is also, like many of us at the university, interested in lifelong learning and actually getting, Rob Brooks says it well on his Twitter handle, he's not so interested in getting people into STEM as getting STEM into people, getting our society to be a society which values scientific thinking. And we do that in collaboration with teachers at schools. I like talking about university lecturers as teachers, and school teachers, primary and secondary, are our comrades in arms with this quest. And Liz has done excellent work. This new science extension program which is a very sort of visionary type thing, is actually very challenging. But Liz is someone who helps bridge this gap, and I think it's terrific. So I welcome all the teachers, all the teachers who have tuned in today. I thank Liz for that work. The final thing I just should say that Liz has also won Australian awards for university teaching. So she's not just a brilliant academic mathematician, physicist. She's also an exceptional university teacher. So Liz, it is 12:07. I've gone 2 minutes over time, something which is very bad of me. So I'll stop now and hand over to you and put myself on mute. Welcome and welcome everyone, and use the chat to ask questions. Over.
Okay, thanks for that introduction, Mern. I'm just sharing my screen now, so hopefully you can all see that. So what I'm going to be telling you about today is several projects I've been working on, where I've been working with secondary teachers to improve STEM outcomes for both tertiary and high school students. So this photo on the right here was taken in the first year physics lab during the Sci-X summer school in January this year. So this group of students was actually working on a project which was run through the School of Mathematics, where they were modelling the spread of infectious diseases, which actually turned out to be a very timely project for this year. So why should we care about how many students are choosing to study STEM? Well, it's widely acknowledged that people with STEM skills are vital for the nation's prosperity and productivity, and it's predicted that the need for these people is only going to increase into the future. However, we have a problem with diversity in people choosing STEM careers, so especially in engineering and physics. So only 13% of qualified engineers are female. Now, this isn't a problem for higher education in general. Across the whole sector, there's 30% more females participating in higher education than males. However, it is an acute problem in physics and engineering. So, for example, in Physics 1A, one of the courses which I coordinate, which is an introductory course which all engineers need to take, consistently less than 25% of the people participating in this course are female. So given that we need more STEM professionals going into the future, it's an enormous problem that half of our society is so underrepresented. Now, physics is an important discipline within STEM. The concepts taught within physics are vital for many professions, such as engineering. And many of the students' final experience of physics is at the end of year 10 science. So if students don't have a good experience in junior high school, which is years 7 to 10, then they opt out of future studies in physics and decide not to go into careers such as engineering or being a physicist. So if we want to improve the diversity among our students at university, we really need to engage more students in junior secondary school. And in order to do that, we need to work with teachers. We need to have really good physics teachers in junior secondary school. So let's have a look at the demographics of high school physics teachers in Australia at the moment. Over 20% of high school physics classes are taught by teachers who are not accredited to teach physics. And some sources say it's even higher, some sources say it's 40%. So at the moment across the country, there isn't actually a shortage of science teachers, but there is a shortage of physics and mathematics teachers. Now, another thing to keep in mind is that there's a really high attrition rate among graduating teaching students. So there's a whole range of values which is stated for this, but some sources say it's up to 50% of teachers leave the profession within the first 5 years, which suggests that possibly training people who already have a STEM degree up to be teachers might not be the most effective way to address this shortage, as many of them will then leave the profession relatively quickly. So in Australia, because we've got such a relatively small population and a really large landmass, there's a lot of rural schools. And in rural schools, the shortage of physics trained teachers is even more dire and acute. So it's not just me who's worrying about this. Last week there was an article in the Sydney Morning Herald, and you can read the title here, 1 in 8 STEM classes taught by out-of-field teacher. So it really is a widely acknowledged issue at the moment. Now, to make the problem even worse for physics, we got a new physics syllabus, which was rolled out to year 11 in 2018. And so the first cohort of year 12 students did it last year, and they're now in first year physics. So this was the first new syllabus that has been introduced in a very long time. The outgoing syllabus was introduced back in 2001. So there's many good things about the new syllabus. It's much more quantitative than the previous syllabus. And it's not contextualized, but teachers need to teach the material within a context to make it interesting and appealing to students. So they need the skills to be able to do this because it's not embedded within the syllabus itself. There's also a lot of content to cover in the new syllabus. So this makes the new syllabus really hard for teachers to teach when they're not confident in the physics. The accreditation requirements to teach physics in New South Wales have also very recently changed. So again, this is a good thing. It's good that we have higher standards, but we do need to help teachers to meet these standards. So in 2019, the requirements for accreditation were increased from 2 to 4 university level physics courses in order to be qualified to teach year 11 and 12 physics. So these graphs give you a snapshot of the people who are teaching and teaching physics. So on the right-hand side, you can see a graph with the number of female secondary teachers and the number of male secondary teachers. You can see across secondary teachers in general, just under 60% back in 2011 were female. So secondary teaching is a female-dominated profession, which is probably no surprise. However, if you look at the graph on the left-hand side, you can see that physics is very dominated by male teachers. So just under 80% of physics teachers are male. A lot of these male teachers are also fairly old. So just over 40% are over the age of 51, which means that they're starting to think about retirement, which means that our shortage of physics teachers is likely to just get worse as these people move out of the profession. Okay, now these graphs show us the number of students and the gender ratios of students who are selecting to study year 12 physics. So these values were taken from the Board of Studies site. So you can see back in 1991 on the graphs over on the left, around about 27.6% of the people taking physics were female students. And over time, this gender ratio has gotten worse and worse, less and less disparate. So by last year, only 22.7% of the cohort of year 12 students were females. What's also been happening over that time is that the number of students who've been choosing to study physics as a percentage of total HSC students has been reduced. So between 2006 and 2010, on average, there's 13.5% of students choosing to take physics. And then by 2019, this was down to 11.4%. Is that right? Did I add those right? Yes. So we've got less and less students choosing to study physics, which is a problem when we want more and more people going into the STEM disciplines. Now, this problem is not unique to Australia. So we've got a graph showing what's going on in the UK here. You can see that in the UK, we've got just under 10,000 female students studying physics for their A-levels and just under 30,000 male students. So again, less than 25% of the cohort is female. In the US, it's slightly different. The graph up the top is showing what's happening in schools, and the blue line is high school physics students, and the red line is, this is the percentage of females as a proportion of the population. So just over 50% of final year students are female, and there's a fairly high ratio of females studying physics, around about 45%. But then when we look at what happens with students choosing to go on with physics at university, we get this large disparity again. So women choosing to study a physics degree in 2017, there was under 2,000 females, while there was over 8,000 males. Okay, so in order to address this shortage of females, we're going to have to address it back in school. And in order to do that, we need to carefully think about, well, what will interest girls in physics and hence in a STEM career? So some research has shown that students' physics identity is strongly correlated with their choice of a physics career. So a physics career here is defined as anything which involves doing some physics. So engineering would count as a physics career. Sorry, engineers. And this research also found that a positive physics identity is correlated with a focus on conceptual understanding and real-world, which is contextualized connections. So girls want to see the connections between what they're learning about and how it works in the real world. Now, these things are beneficial to both males and females. So good teaching is good teaching and benefits everybody, but it has a disproportionate effect on the female students. So though they were sitting in the same classes, females reported experiencing a conceptual focus and real world or contextualized connections less frequently. So for girls, we need to make these things more explicit and make sure that we do them more often. So this study actually interestingly found that having female role models didn't have much of an effect. Other studies have found that it does have an effect. So it's debatable at the moment what role female role models play. So my personal theory is that rather than showing lots of female role models, it's probably more useful for females to illustrate that science these days is actually done in teams. I think if we think about physicists, we tend to picture Albert Einstein or Sir Isaac Newton, and the image we have of these people is that they're a lone genius. I mean, I think everybody's probably heard with the pandemic going on that Sir Isaac Newton came up with his theories while he was in quarantine due to the Great Plague of London. So he did come up with these theories in isolation, but that's really not how physics is done these days. These days, people work together as teams. So I've got a photo of my group here. And I think that promoting this lone genius story as the only story that high school students see probably turns girls off physics. So a possible solution to addressing this teacher shortage is an online graduate certificate to teach physics to science teachers. So because it's online, it's easy for the rural teachers to access. It offers flexibility for teachers because they're very busy people. They've got family life as well as full-time work, so they need to be able to fit the degree around their lives. And as it's offered to practicing science teachers, it means that they've already studied how to teach science at university. So they've already covered the science methods. All they need to be accredited is to learn the physics. So they need 4 physics courses in order to meet the accreditation. So when we were designing this degree, we put teaching tips on how to teach this material to students. We embedded that within the degree rather than having separate courses on how to teach this. Okay, but if we're going to introduce an online degree, and because it's very relevant with the current pandemic, I think we need to think carefully about, well, does online education actually work, or are we disadvantaging students by making this degree online? So there's been a fair amount of research done on this. I've also done my own research where I've compared a face-to-face course that we offer here at UNSW in Introductory Physics with an online course that we also offer at UNSW. And for these courses, I've measured the learning gains. So the learning gains tell us how much the students know at the end compared to how much they know at the start. We subtract those two from each other, and then we normalize it by dividing by the possible amount students can learn. So these two cohorts tended to consist of students who were fairly similar to start with. They had very similar pre-test scores. And what we found was that the learning gains in the online course were slightly higher than the learning gains in the face-to-face course. And the face-to-face course had, back when we had 12-week terms, it was 6 hours face-to-face each week. So it had a large time commitment. And you can see what's particularly interesting is that the female students actually did slightly better in the online course, while the male students did better in the face-to-face course. And by better, we mean learnt more as measured by learning gains. And I attribute this in the online course to the contextualization of the course. So this was called Everyday Physics, and each week we looked at a different, how something different worked, like how a hot air balloon worked, and then looked at all the physics behind it. So online education can work. We're not doing a bad thing to these students by making this degree online. Now, the other really important thing is to have input from high school teachers. So I have actually been a high school teacher after completing my PhD. I worked for a couple of years as a high school teacher before coming back to UNSW to be the first year physics director. So I do know what it's like to teach in schools. But as well as getting my input, I introduced a visiting teaching fellow program where we get a current high school teacher to work with us in the School of Physics for a year. So they're seconded for a year. They teach first year classes, and they also help us develop outreach materials. So this was based on a similar program in the School of Maths. So far we've had 4 teaching fellows: Ingrid, Jess, Troy, and this year we've got Michael. So I'll be showing you what they've done throughout the rest of the talk, but getting the input of current high school teachers into a degree to teach physics to teachers so that they can teach it was really, really important and really, really useful. So the degree is structured into 4 courses because that's what the teachers need to be accredited. The first course is called Everyday Physics for Teachers, and it's predominantly about waves, but it's very contextualized. So it shows teachers how they can contextualize the material to make it interesting for students. So this runs during UNSW Term 3 and summer. These were chosen because our Term 3 tends to correlate to school Term 4, and teachers tend to have a slightly lower workload in Term 4 because the Year 12 students have already graduated and left, so they've got a little bit more time then. But if they want to complete the degree in a single calendar year, they can start it in summer, in which case this first course runs in a compressed mode for 5 weeks. The second course is mechanics for teachers. Then we've got electromagnetism for teachers, and modern, which is quantum mechanics, and thermal physics. So I developed the lecture material for 3 of these courses, and Ingrid Mendez, who was our teaching fellow back in 2017, developed the lectures for the electromagnetism course. Okay, so even though it's online, it's really important to try and keep the students actively engaged. So to do this, we use the Open Learning platform because it's visual, and there's forums at the bottom of every page where the teachers can ask questions if there's anything they're wondering about. We developed a series of icons to indicate to the teachers what they should be doing at that point. And this also helped us during the design period to make sure that we had useful activities spaced through the course, getting the teachers to actually make use of what they were learning along the way. Now, an important question to ask when you're putting a degree online is, should we go with asynchronous or synchronous? So the big advantage with asynchronous is that it's very flexible for students, because it means students can log in whenever they want and they can fit the course around their schedules. So there was a meta-analysis done of online courses, and it found that there was a slight, very slight positive effect for asynchronous online courses and a slight negative effect for synchronous online courses. When we first introduced this degree in 2018, we did have 3 synchronous weekends. So the students came in for 3 weekends during the course to do experiments in our lab. This was really quite hard for the rural students who had to fly in or drive a long way and arrange accommodation. So then in 2019, last year, we moved all the labs online as well. So from last year, the instructions for the labs were online, and the students conducted those labs with equipment that they could source from their schools, which actually had other advantages as well, because it meant that they could then use what they were doing with their own classes because they had access to all that equipment. So if you are thinking about moving courses online, which I'm sure lots of you are at the moment, I'd recommend don't just replicate face-to-face teaching. If you are having synchronous components, which can be very useful, just make sure that there's a real reason to have those and that they are very interactive. They're not just students logging in to watch somebody speaking at them like I'm speaking at you now. And the other thing which it's useful to consider is think about your students. I'm definitely not a night owl, but I know most of my students are. When I look at when they're using resources, most of them are using them really late at night when I'm asleep. So having the lectures online means that they can watch them when they're awake, and it means that I don't have to give them when they're awake because they're already up then. So the lecture material in this online course is delivered through videos. So I tried to make the videos relatively short. They tend to comprise of 3 different components. So I'll have me explaining theory, and as I explain the theory, the equations and important words pop up on the screen to help reduce the cognitive load for the students. The videos also have worked examples to show the students how to put into practice what they're learning. And then we also have demonstrations, because demonstrations are really important in physics. It really does apply to the real world. And in this course, when we're doing the demonstrations, we also talk through how you could set up this demonstration to use it with a class. So I was very lucky to have help editing a lot of the videos for this course. So Bryony Lanigan and Elliot Griffiths, who were past physics honours students, helped a lot with all this video editing. And here you can see the film studio that we have in the School of Physics where we made all of these videos. So how the course looks to students is they'll have a video and then they'll have a question or activity that they can do. So you can see here's the question, and then the students post up their answers to the question. There's quite a few questions through it, and because physics is fairly quantitative, there are quite a few problems that you need to be able to solve. The students post up their answer and then they can check it. And if they get it wrong, they can watch a video solution showing them how to solve that problem. In each of the pages up the top, it clearly tells them what they need to learn on that page, why they're doing it, and what they need to be able to do by the end of this page. Okay, so unfortunately, assessment does tend to drive learning. So the assessments for these courses, 30% for most of these courses is for the experiments. So we've already discussed those. They do these at school. And then as well as submitting their experimental results, they also need to submit a worksheet, which they could use with a class, which is related to the experiment that they've just conducted. We also have online quizzes. So these are delivered through Moodle using stat questions. So these quizzes are to give the teachers lots of practice solving questions. So they can do these quizzes as many times as they want. They're pulled randomly from a large bank and their highest mark counts. We've also got a final exam. So when the university campus is open, they can choose to take this during the exam period on the university campus, or they can take it invigilated at their school, as schools are very used to invigilating exams. Now, there is support for students enrolling in this program. The Department of Education offers a sponsored training program which covers quite a lot of the cost for students working in Department of Education schools. So those are public schools. For the teachers teaching in private schools, quite a few of them persuade their principal to cover the cost of this degree for them. The teachers who are just finishing and don't yet have a permanent job often have to cover the costs themselves, and they do that because with a physics code it's much easier to get employed. Okay, so does it work? Well, in 2018, 4 students graduated from the degree, and then that was the first year it was offered. In 2019, the second year, we got 9 students who graduated from it. So I emailed all our past graduates about this talk and asked if they'd be willing to answer the following questions. So I asked them, how has completing this degree impacted your career? What was worthwhile about the degree? Would you recommend the degree to other teachers, and if so, why? And is there anything else you would like to share about the program? And of the 13 eligible graduates, 8 of them sent responses that they're happy for me to share with you. Okay, so please don't read all the words on the slides. I'm going to read out the bolded bits, which are the important parts for this talk. So first evidence that it's working is that the graduates are actually getting jobs. So here we've got Andrew, who was part of the first cohort who completed the degree, and he said that completing the degree gave me the qualification I need to teach at another school. I have no doubt that the degree helped me get a job elsewhere. So Andrew's teaching, he moved from one metropolitan private school to another metropolitan private school. Okay, Jess is teaching at Orange High School. So she's a rural teacher. And she said, firstly, I was awarded a STEM scholarship and was hence awarded a permanent position at the school I've been working at for the past 5 years. I now find myself in a position where I'm highly sought after employment-wise and am able to provide support to a wider range of students. Okay, and Katherine, who was also in our first cohort of students, now has a permanent job at Murrumbidgee Regional High School. And she said, I've now got a permanent teaching job thanks to having my physics code. So it's working for our students that way. Now, the other thing we said was that we had to improve the teaching of junior science to increase the number of females who are choosing to study physics at years 11 and 12, and hence entering into that STEM kind of pathway. So James, who graduated in 2019, said that it's improved my teaching of many concepts to my junior classes, which is stage 4 and 5. So in getting females to engage in physics, we saw that 2 important things were a conceptual understanding and also contextualizing it and making it applicable. So you can see that James believes that this degree has improved how he teaches the concepts. And similarly, Derek says the course also has made stage 4 and 5 physics content much more enjoyable, seeing applications and being able to see deeper links between concepts. So he's giving his students a clearer conceptual understanding, and he's also contextualizing it for them. And then Lane commented that it also impacted how she teaches maths. So showing students where the application of concepts can be applied, not just in science, but also mathematics. Now, teachers really appreciate the relevance of the degree. So they appreciate that the assessments, such as doing the experiments and producing the worksheets, are actually applicable in the classroom. So Lindsay said that it's a worthwhile degree. My husband teaches physics, and it also helped him with a few new parts of the new syllabus. So very well mapped to the new course. And James said, I like that the course was tailored to teachers. The resources that I developed for the experiments in each of the units have been shared with my colleagues and will be useful for my own teaching in the future. And Jess said, I absolutely loved how relevant the content was made to high school teaching. And Derek, this course taught content which was extremely useful and transferable to teaching in the classroom. Having a specific course like the one provided by UNSW meant I knew exactly what was required of me, was consistent and knowledge and practical based. The degree was online and the assessment resulted in me walking away with practical write-ups and tasks I could immediately take into the classroom. These were much more useful in application to the classroom than lesson plans and vague research-based analysis of pedagogical strategies. Now, the course is also very flexible. Last year, we had a couple of students who completed the course while they were on maternity leave. So you can see Mary here with her son, Ben, who was born during the course. And Mary said, it has added more value to my portfolio in the industry where physics female teachers are scarce, which we saw from the graph earlier is definitely true. And she can be confident that when you have learned it, very applicable as soon as you are out teaching it. And Lindsay commented, the course gave me something to focus on while on maternity leave. In many ways, it kept me sane. Can't thank you enough. And I can personally relate to this one, having taken up a lot of craft while I was on maternity leave to keep myself amused. I think this was probably a more useful use of Lindsay's time. Okay, so besides the graduate certificate, our teaching fellows have also worked with me on several projects to impact on how science is taught in high schools. So the new syllabus was introduced in 2018, and from discussions with Ingrid, who was our 2017 teaching fellow, it became clear that what those teachers were most worried about teaching was the depth studies. So depth studies were 15 hours that students were meant to spend on a research project. So this wasn't just in physics, it was across all the sciences. So we actually got a CEF grant up across the Faculty of Science to develop materials to assist teachers in teaching these depth studies. So this included many academics, including Alistair Poole from Bees, Louise Lutziman from Babs, Angela Maharaj from Climate Change in Bees, and Scott Solway from Chemistry. And we produced 18 depth study modules, which we share freely with teachers. So if you want to see those, you can access them on this link here. And some of our PhD students talked about their research and how it related to parts of the syllabus. Our 2018 teaching fellow helped develop excursions for high school students. So because our first year physics lab is not used much out of term time, Jess said that a real challenge for a lot of schools is finding enough equipment for classes to actually do experiments. So often with this equipment, a school will just have one set, so it'll be more of a demonstration than an actual hands-on activity for the students. So we realized that we had full class sets of lots of the equipment and that our lab wasn't being used for a lot of the year. So we developed a series of excursions that schools could sign up for. So as well as doing experiments in our lab, the school students got usually a short talk from a researcher and also a tour of some of the research labs. And they found this very valuable. So one of the teachers commented, it helped to give our students a taste of campus life. And the students found it useful as well. One of the students said, the appeal of a career in physics/engineering has expanded for me thanks to today. Yeah, a really big project that we worked on last year was the introduction of the SciEx program to support extension science. So there was lots and lots of people involved in this. The executive team was myself, Laura McCamish from chemistry, Shannon Maisie from chemistry, and Troy Garrett, who was last year's teaching fellow. but every school in science contributed a project to it. And each of those projects had a PhD student mentor and an academic. We also had one of the schools in engineering contribute a project to this. So how this worked was students got some information online from their mentor about the area that they were interested in. They chose a topic from a list that they were interested in and were assigned to this group. And then for 1 week in January, they came to campus and worked in a small group with their PhD student mentor on the project, collecting the data and everything that they needed. And they've now returned to their schools or working from home, depending on exactly which school they're at. And they're now writing that up as a report and getting help from their PhD student mentor. So we had 65 Year 12 students complete this in January last year, who are currently working on writing this up. So I think this is really important because it really shows these students how science is done, and they can see how the PhD mentor works with their own supervisor. And so science really is done in teams, not as individuals. Another thing that we're working on is, this is my group here, Physics Education Research for Evidence-Centered Teaching, or PERFECT. We work with undergraduate physics and teaching students. So Sam here is in the 3rd year of his physics and education degree, and he's doing a research project with Christine. And one of the things that we do is we have a fortnightly journal club where we discuss topics in physics education, and we make this open to undergraduate teaching students. So a number of these come along to those journal clubs as well and learn about what research tells us about good physics teaching. Okay, so in conclusion, I think the important points are that online education can work, that we should work together with each other and teachers to improve STEM outcomes and to decrease the gender disparity. And I'd really like to say big thanks to everyone. There's so many people who've contributed to these projects and also to this presentation. Okay, so I think that was everything that I needed to say. So I'll open it up for questions now.
Wow. I just have to say, wow, Elizabeth, Liz, you should be in charge of acronyms. The Physics Education Research for Evidence-Centered Teaching, perfect, is pretty cool. It's actually one of the best ones, because most of them are so, I mean, that one is obviously a little bit contrived, but it's so cool, whereas a lot of them have to struggle a lot more. So a few questions have come up in the chat, but I've just got to ask you, because I'm itching to ask you, I'm pushing in, but I couldn't believe the numbers in the US graph that you showed. You showed that in high schools, it didn't seem to be much of a problem. And then you went on to the undergraduate degree and said, look, the problem manifests itself there. But what's the difference in the US?
I don't know. I've written to people in the US last week to try and work this out, and I'm not sure. Like, I don't know if they're doing more subjects in high school than we are, so maybe they're more likely to choose physics.
Yeah, I think that like the high-end colleges require physics, and so then the high schools have to offer physics, and then it's considered, oh, it helps you get into college. But then they don't take physics once they get to college. Yeah,
got it. It's required for university entry, and that will do it. It's the same in Australia. If anything's required for medicine, everyone does it, or many people. Got it. So thanks, Susan. Look, let's, Liz, do you want to go down the questions that are written, and then we'll throw it open to other questions? Over.
Yeah. Yeah, I'm just trying to work out which ones are questions and which ones are comments. Okay, so nice looking interface. What platform is it built on? So the graduate certificate, the learning materials are all delivered through the open learning platform. Oh yeah, which people have then replied to. Yeah, do you have any information on the major contributing factors to this attrition rate? No, I think, okay, I suspect, but I haven't read a lot of the literature on this. It's quite hard when you're a first year out teacher to get a permanent job. You need to do quite a lot of casual work, especially in the public system, before you've been like up the list far enough to get assigned to a school. Casual work, speaking from my own experience, is very hard. There's a lot of classroom management involved in that, which is quite daunting as a new teacher. So I suspect that it's just that a lot of teachers get turned off by that initial casual work. And for physics, it is much easier to get a permanent job earlier than in the other subjects. So possibly that's less of an issue for them, but I haven't read up on that too much. Yeah, is the graduate certificate ongoing? Yes, so the graduate certificate is ongoing. We're into the 3rd cohort at the moment, so they've just started the 3rd course now. It runs in term 2, but we've made it available for them so they can get ahead if they want to. I think that's all of the questions.
There was one about attrition rate, Liz, if you just go up, which was the stat you quoted about 1st to 5-year attrition among physics teachers is interesting for me and McAdam.
Yeah.
Do you have any information about that?
No, I mean, the attrition rates are stated very differently in different resources. That wasn't specifically for physics teachers, that was for teachers in general.
So look, I want to jump in again and just say a couple more things. The 65 science extension, hooking up the students with, linking them up with PhD students, that is such a great idea. I think, you know, that was an interesting visionary course. And I have to say, they consulted me a couple of times. I was a little bit worried about how well it would work, but it looks like UNSW is making a huge contribution there, and it's a model for everyone. So I was just delighted to see that. The question I had though was actually with your physics teaching course, what's the size of the enrollment and the economics? I mean, that's a typical bean counter question from me, but you know, the bigger it is, the less we have to charge, the more opportunities. And you know, I just wondered, I didn't really get an idea of the numbers. Over.
Yeah, so it's been growing. I mean, the first time it ran, we had 4 people who graduated. The first time it ran, you could actually be accredited to teach physics with just 2 physics courses, because that was a recent increase in what was required. So a few teachers left that cohort after doing 2 courses because they were qualified to teach it. Last year, we had 9 students who graduated. Currently, in the 3rd course in the degree, we've got 15 enrollments. So at the moment, all the students who are enrolled in this degree are from New South Wales. So I think the easiest way to expand it is to get students from interstate, because it is online, so they can do it interstate, but I don't really know how to market it interstate.
That's interesting. So yeah, we should probably see if we can get our marketing folks onto this, because it's so important. It's really interesting to me. The other thing you said, which is right, that there's not really necessarily a shortage of science teachers, but there's a shortage of physics and maths. And I hear this all the time. There's not really a shortage of STEM. There's a shortage of physics and maths. And what you said about how often those courses are taught by people, good people who, you know, help out by teaching them, but they never really train to do that. But there's no one else in regional Australia. It's an enormously important service. So that's good. So we can touch base about that and talk to our marketing people, because I think we should promote this. Now there's a facility people can either put up their hands, I think, or they can just jump in. So I'll just shut up for a moment. If anyone wants to jump in and ask the question, over. But it's tricky, isn't it? Because no one knows when to jump in. But when you've got a microphone and things, there's a bit of hesitation, and then you catch someone's eye. There were 46 of us at the thing, 45 now, which is very good. We've still got a few more minutes. I know people will have other Zoom minutes at the stroke of one. I do.
Merlin, there's more questions in the chat now.
Oh, excellent. Thanks, Chris. Oh, yeah. Over to you, Liz.
Okay, so from Julian, sorry, my question is slightly off topic. Have you trialed your online lab experiments for outreach, e.g. webinars to attract year 11/12 students to science? Yeah, we haven't, so far we haven't run online labs much for outreach. We've been trying to get them on campus so that they can see like the UNSW campus. But this year's teaching fellow, Michael, was working on getting more resources for high school students online, because especially like that's very relevant and important for now. So not right now, but we're in the process of doing that. Richard, what makes you the most optimistic, Liz? Well, I mean, all the teachers are actually enrolling in the degree. The teachers want to be better physics teachers, so they want to learn this stuff, and they really engage with the materials when they're doing the degree. So I think like they all want to be good teachers and just want something like this. With existing physics teachers and this online course, would they benefit from studying it? If you're at all rusty in physics, then definitely this gives you, like, it shows you how to connect this to the real world and covers some teaching tips as well. If you're already accredited to teach physics, then it won't help you that way, but I still think you get a lot out of doing it, I hope.
Liz, can I ask you? That's great. I think it's. I love the way you structured your talk, actually, with the problem and what you were doing and the solution and the endorsements at the end. I thought it was fantastic, and seeing people getting jobs, and then people who study online because they're on maternity leave or they're regional. I love the way you did that. I want to ask you a question. So I know Joe Wolf in your school, was a pioneer with PhysiClips, and then he did the MOOC and those sort of things. Are you using the same studio, and were some of those learnings helpful?
Yeah, so that studio, which was pictured, was paid for through Joe Wolf's OLT funding to develop the PhysiClips materials. So yes, yeah.
Look, that's just great to hear. It's interesting. I've always been a MOOC skeptic, actually, but I always felt there was worth making an investment because it would enable us to pull ourselves up by our bootstraps and get to the time. And so it has in your school and the culture.
Yeah, so the particular, the most useful point of that MOOC was the MOOC which Joe developed was very similar to the first, say, 1/3 of the Physics 1A course. So 2 or 3 years ago, we constructed web stream lectures for Physics 1A, where the students could choose to do their lectures online. So it was set up very interactive, short video question on Moodle. And that has been absolutely invaluable in the last term, as you can imagine, because we've already got all our lecture material online and we can see who's engaging with it and reach out to the ones who aren't. And yeah, so that's been useful.
That's so cool. I think, I'm a MOOC skeptic in general, but Joe's stuff, I actually looked at some of his PhysiClips and stuff, and they were enormously impressive, but they're quite hard. He just intuitively, when he ran through the answers, it made it seem so simple, but I don't know, my physics was too rusty. What's another, there's another question that's popped up, Liz.
Could this course be a direction towards STEM teaching learning in schools? I'm not 100, I may be misinterpreting this question. So I think maybe this is asking, like, could this course also help with the school students? I think so. I mean, all the videos that we've created for this course are available for free on YouTube. So if you just go to the UNSW Physics YouTube channel, you can see all the videos. And I think a lot of them could be used with Year 11 and Year 12 physics students as well to help with all the students learning at home.
That's great. So look, I think we should wrap up like we would at a lecture at 5:02. I just want to thank you, Liz. I really enjoyed it. I think you presented it terrifically well. Your slides were great. It worked. The technology worked. It's great. So many people came. I've got a counter though. We're down to 38. So some people are leaving to their next meeting. Thank you, everyone, for coming. Thank you, everyone who engaged in the chat. I think some people were a bit shy about engaging in the chat or turning on their microphone, or they're still in their pajamas and didn't want to turn on their camera. That's the new normal. But thanks, everyone. Thank you, Liz. I think it's been a great occasion. Thanks, Remy, for organising it, all the people from PVCE that have supported these, and thanks to all the members of the Scientia Education Academy who are really showing leadership. And the only way to lead in academia is to lead by example. And this does elevate the student experience, not just for us, but for high school students. So thanks very much. And well, I'll say goodbye.
Thanks for listening,
Bye.
everybody.
Thanks, everyone. Bye.